So far is that we gave an introduction about how fission energy was discovered by humans. Just pass it around. We digressed. We learned how to access the data in the information age. The terminology is mining for data in a data warehouse, and that was a table of the nuclides. Then we went and explored the particulars of the strong force which keeps the nuclei together. And this is a secret for releasing fission energy, but also fusion energy. So today, we look at what are the implications of fusion energy. Now, fusion energy so far is used in thermonuclear weapons, but in our future, there are already experiments that would try to control fusion. And in that case, it would supply us with, for humanity, an unlimited supply of energy, as some people do think. So in that case, I would like to be able to start recording back again. And oh, it is recording. Wonderful. So I'll start sharing the screen. And the chapter that we are going to cover today is how to, what happened beyond the discovery of fission. And that is a chapter that I'm going to title as the nuclear world. So let's see what happened after nuclear energy was discovered and used through the fission process. Immediately, scientists realized that humanity has discovered the mother of all energies, if you want to call it. Energy in general has usually a basis in nuclear processes. Think about the stars, and particularly our star, the sun. The energy is nuclear energy. It's a fusion of the nuclei of hydrogen, so it's through a set of chain reactions that eventually turn the hydrogen, the most common element in the universe, into helium-4 and other elements. So you find that nitrogen and carbon also exist in the reactions that happen in our star, the sun. That energy comes to Earth and it's turned into other forms. We use, of course, light, the electromagnetic spectrum. The process of photosynthesis grows plants. Then plants grow both on land, that is the basis of coal, and then they also grow in the oceans, in the water. Notice that most of 78% of the surface of the Earth is water, really. We are a water planet. Plankton grows and the marine animals, and then they turn into petroleum. So when we talk about our major energy sources today, whether it's coal, hydrocarbons in general, coal, natural gas, and petroleum, they have their origin in nuclear processes in the star. We also have another nuclear process under our feet that it could be a source of energy, particularly geothermal energy, which is radioactivity, and we'll devote a whole chapter to these processes. In the nuclear world, immediately after the discovery of fission, the Chicago Pile #1 and the use of fission energy in the atomic bombing of Hiroshima and Nagasaki in Japan, humanity's survival instinct, in fact, led it to try to sublimating the new state of knowledge. The terminology here could be from the Holy Bible, turning their swords into plowshares. That refers to the Israelites getting into the Holy Land and turning their wartime tools into agriculture, plowshares, peaceful tools. So the idea of peaceful application of nuclear energy became the standard here. And still the danger, and we live it today. A possible nuclear war can basically, it's an existential kind of risk, can end up our technological civilization. And so humanity also concentrated on trying to control the use of nuclear weapons through different treaties and international agreement. So I would like you to read whatever I'm not covering today in the chapter along this line. This shows us, of course, here a sequence of pictures on how the events progressed in the Trinity test. Trinity test was the first nuclear test of a nuclear device conducted in the desert of New Mexico at Alamogordo. And you could see here the progression. It was exploded on top of a tower to maximize what's called the stem effect right here. You could see it forms immediately a large fireball. The fireball is ionized gases. When gases are hot, they rise through buoyancy in the atmosphere. You could see that fireball there rises, but then it generates also a shock wave, or a blast as it's called. The shock wave hits the surface of the ground from the top of the tower. It would be positioned right here, and then reflects back, and the reflected wave through interference and the incident wave together form what's called a stem. And that stem propagates a shock wave horizontally, and it becomes extremely destructive, as I'll show you later on. So it's like a piston hitting the any structures like homes or bridges or any human structures. It was extremely destructive, and typical of in that case is that fireball falling, rising up and sucking up the ground. So it forms what is observed as a mushroom. Actually, it rises and then comes down back again. It rotates in a toroid of revolution, like a torus or a donut, if you want to call it this way. This is one of the color pictures, the only color picture actually taken of the explosion when it happened first at Alamogordo. It was a plutonium device because the people who designed those devices realized that when they produce plutonium-239, it comes mixed with plutonium-240. And if you go to the chart of the nuclides, you'll find that plutonium-240 has a characteristic where it spontaneously fissions. It fissions all by itself. So in that case, they needed to implode the device. They couldn't simply bring two subcritical masses together like if they would have used uranium-235. And it became some kind of an important event in the life of people in the United States. So you could see here historically, people in Nevada gathering with their pickup trucks and cars on top of a hill and watching those tests in the Nevada desert. Not only that, but here is a mother and her son watching actually a nuclear explosion from Las Vegas in the Nevada desert. The first testing occurred in the atmosphere. So the products of the explosion itself and the neutrons also turning dust and the materials of the device into radioactive material, they were not understood at the time. So the testing was, as you could see here, in the atmosphere. It became a very kind of interesting situation while nuclear testing was going on here up in the atmosphere. You find here that young lady dancing a ballet, and another time here, maybe it's the same explosion, another lady having a cotton kind of a dress there. And it was some kind of very romantic, or I would say glamorous, atomic bomb ballet in that picture. And this is Miss Lee Merlin, simply given the title of Miss Atomic Bomb in the Nevada desert. All right, so that was among members of the public. The military became extremely concerned about a possible attack on a fleet of ships in a harbor. Well, that's what happened in Pearl Harbor that started the war with Japan, the attack on Pearl Harbor. So they gathered a collection of Second World War ships that were basically either discontinued, really. They were going to be mothballed on an island in the Marshall Island, actually an atoll. What is an atoll? You could see here, if you look for the picture here, This is a coral reef that grows up, forms some kind of a big circle with an opening to the ocean. It's named an atoll. The inner part of it is protected from the waves from the ocean. So fishermen like to harbor their boats inside the atoll. And that is one of the atolls in that area called the Bikini Atoll. And the name was adopted by some French basically fashion tycoon, and he named the dress at the swimming dress bikini, and the name stuck to it. You could see here the different ships, mothballed ships that were tested just to see what is the effect of an underground explosion on a fleet of ships, and that became named the Crossroads sequence of tests, or in the Bikini Island. You could see there that a huge ball of fire is generated. A shock wave can be seen here, and this is a view 1 mile away maybe from the explosion. You could see that it generates a stem. The water simply rises up to the point of carrying out a whole ship out of the water. So it was definitely very destructive. So imagine basically you're being on a ship, and it doesn't need to be exploded up in the air. It's underground explosion here. It generated energy in the same range as the bomb that was dropped on Nagasaki, about 21 kiloton, or 1,000 tons of trinitrotoluene, which is a basically a high explosive. The name given to it was Crossroads Baker, and they used 96 decommissioned naval vessels. Some of them were American, some were Japanese, some were German, and that happened in July 24, 1946, almost 11 months after the bombing of Hiroshima and Nagasaki. This is some video grabs taken from a movie. You could see the explosion happening underground. A fireball forms, it pulls up the water up, and they sent it up into the atmosphere. Then the water that has been raised starts falling down again. I call it the stem. And as it falls down, you could see that it can raise the ships out of the water and then drop them back again. I show that particular picture here is really sobering. You don't want to be in a fleet of ships that is targeted by these nuclear explosions. The water column was hollow in the center. We cannot see it from here. And it was about 610 meters, half a kilometer in width. And it lifted 2 million tons of seawater. And the surge rose up to 274 meters and created a tsunami 5 meters in height that hit the ships that were away from the center of the explosion. As they carried out those tests, they tested the effects of radiation on animals. You could see some goats here on some ships to study. They didn't know about the effects of radiation, and they even tested it on humans. They didn't know also the effects of radiation at the time. It was bad learning of the process. These are newly declassified pictures of those decommissioned ships used for nuclear testing by the United States Navy. And the effects of nuclear weapons are really devastating. Look at here, the surface of an aircraft carrier. The surface of aircraft carrier usually is made out of wood so that they can take the impact of the plane's landing. And that's the Independence aircraft carrier. So it's a single device up in the air can totally devastate here. As you could see, that was a test carried in 1952, totally destroy an aircraft carrier. Another aircraft carrier, simply, you could see it's sinking here. That's a Saratoga aircraft carrier. After 8 hours of an explosion on top of it, they called it the Gilda device, 150-meter explosion above the deck with planes on top of it. Eventually, it sank. So the military as well as civilian population understood the energy that can be released. Just historically here, that is a battleship that was too old to be used, obviously. Pennsylvania was also among the 96 ships. That's a Sakawa, that's a Japanese ship. And here, that's a Nagato. The Nagato was the largest cruiser ever built, huge, built by Japan. This is Prince Eugene, I think that's a German ship, Prince Eugene, and it sank there in the atoll. And you could see the propeller of the ship here. It is some kind of a paradise for scuba diving enthusiasts because it became a harbor for fish to grow into it. They tried to decontaminate some of the ships, bringing in maybe firefighting type of tugs and spraying the surface of the ship with seawater to get rid of the radioactivity that would have covered it unsuccessfully. And in that case, any fleet that is subjected to a close-by nuclear explosion is basically damaged toward beyond recognition. What I didn't know is how they affect humans. So in some cases, they used basically dummies or mannequins here. You could see at several different distances from an explosion in the desert. And they also asked troops to hide maybe in a trench while the explosion is going on, and then move in the area of the explosion, unknowing, not knowing about the effect of radiation. Air Force personnel, as we could see in those pictures, were asked to watch the explosions. They wore ski masks, actually, to protect them against the ultraviolet from the explosion. They were asked to watch it. These are also sailors on a ship asked to watch the explosion. It is not just the light or the shock wave that results from these explosions, but also we get gamma rays, and that's electromagnetic radiation, as well as neutron radiation. So those people were damaged, unfortunately. Eventually, they got maybe some cancers in their older age. Here are troops that you could see. They were these are now army troops. They were asked to watch from trenches and then move into the area of the explosion. So there was lots of unnecessary testing on human being at the time. The war, in a way, continued even after it was ended. Another aspect of the testing that went on, so this is a period of testing and under different conditions, is when you explode a device up in the atmosphere. If you explode the device up in the atmosphere, it doesn't, the shock wave doesn't, it reaches eventually the ground, but the mushroom effect is very minimal, but it creates what we call an electromagnetic pulse. And the electromagnetic pulse is basically a large generation of electrons from the fission products and from the explosion itself. These are trapped in the Earth's magnetic field, and they generate a huge, very powerful pulse of electromagnetic radiation, similar, but many much more times stronger than lightning. And in that case, the electromagnetic pulse is so strong that it can destroy all the electronic devices in a whole continental United States with a single weapon exploded up in the air. So this is high altitude airburst sequences. You could see the mushroom is trying to form, it's even though it's high altitude, but if you go to very high up in the atmosphere, the explosion looks more like a ball. It looks like almost like human here. This is an explosion up at high altitude, and in that situation, we have to deal with what's called the EMP, electromagnetic pulse. Some explosions happened in the Pacific, and it resulted because of the electrons trapped in the atmosphere are similar to the situation where we get the northern lights or the aurora borealis. This is what they observed from the islands of Hawaii, 1,000 miles away maybe. And they also lost some of the lights in the street. So testing of these weapons basically proceeded up and on land and in the atmosphere. You could see here that they tested it at Air Force. Basically, personnel have been tested. They were asked to watch the explosions to see what are their effects. This is another situation where they exploded a device that up in the air here, and they had some personnel standing on the ground right under where the explosion occurred up in the sky. You could see the first thing they feel, because light from the explosion travels at the speed of light. So they see a pulse of light, very, very bright, brighter than the sun, in fact. And then after they get the pulse of light, they get the gamma radiation, but then comes the blast wave. The blast wave is a shock wave, a piston almost, and you know that sound travels at the speed of sound. So after they are subject to the pulse of radiation, neutrons and gamma rays, they get the blast wave. And this is apparently the origin of the terminology ground zero. So when you hear the word ground zero, it's a point really where an explosion would have happened. They call themselves a ground zero population. That was now a miniaturized device. It was not the 21 kilotons of Hiroshima, or sorry, the 21 kilotons of Nagasaki, or the 15 kiloton of Hiroshima. That was an explosion of 2 kilotons only at 10,000 feet. So the whole process was miniaturized. It was also turned into artillery kind of shells. So this is a nuclear device as an artillery shell with a large cannon tested in the Nevada desert again. That one was 15 kiloton of TNT equivalent, and the device was named the W-79. W and number here is the designation of different shell configuration. What happens as a result of nuclear explosion was also tested on structures. So this is a home built especially for that situation. At 1 mile away from the explosion on this side, you could see that the first effect is a light pulse, but then come the X-rays. The generation, the device produces lots of electromagnetic radiation in different parts of the electromagnetic spectrum. Part of it is light, part of it is X-rays, gamma rays, and then come particulate matters like neutrons. You could see here that initially it's a pulse of light followed by X-rays. The X-rays are absorbed in the structure, and that basically generates a fire. So the whole house here, if it is subjected at 1 mile from the device explosion, catches fire. Fine, okay, so it caught fire, but that's not enough. Then comes the blast wave. And the blast wave comes initially as a compression wave. Let me show you what it looks like. So if we generate the blast wave here, you find that it comes with a rarefaction, then you get a compression. So here is almost like a piston moving in this direction. So if you have, say, a little tree here, it will bend in this direction, but then comes the rarefaction and bends it in the opposite direction. So you have something now that, like when you try to break a wire, you subject it to fatigue loading or cyclic loading, you bend it in one side, then in the other side, and that's what happens by the shock wave. It compresses initially by the piston, and then it pulls it out in the other direction. You could see here now it's pulled to the other direction, and the whole house simply literally disintegrates. This is video grabs from a movie. So it's really, really destructive. First, the effect of the X-rays, and that turned the whole thing on fire. And then later on, it simply disintegrates it by compression, then compression loadings and tension loading. You could see here what happens even to trees. They are bent in one direction as they have been set on fire and then pulled in the other direction. And radar equipment or equipment on ships, as you could see, this is a radar here, is totally destroyed in a blast of an explosion. So that test showed how damaging fission devices in that case are. Then came an idea by one of the scientists, Edward Teller, at the Los Alamos National Lab on using not just fission, but also combining it by fusion. And he had the point that fusion occurs in the stars, and fusion would occur between the light elements, the equation that I gave you last time, between, say, hydrogen isotopes like deuterium and tritium, and they're much lighter, so we can put in lots of material to generate fusion energy. The project started at the Los Alamos National Laboratory. It was opposed by Robert Oppenheimer, because Robert Oppenheimer thought that the energy that is being released by fission is enough to destroy lots of structures. And he suggested that maybe at 100 kiloton of energy, you can destroy any bridges, any fortifications used by the military. There was no need to try to go to higher energies. And you'll see later that higher energy goes into the megaton, or instead of kiloton or thousands of tons, that's now millions of tons. So we increase the yield or the destructiveness of those devices by 1,000 times. So it's a huge jump in the energy release. The project was given the code name, the Super Project. And in that case, the effect, the problem was how to compress a mass of hydrogen isotopes, deuterium and tritium, because we couldn't really compress hydrogen like in the stars. That would take a time constant that's much longer than if you compress deuterium and tritium. You'll see later why that is so when we cover the topic of fusion. And the compression had to be done with radiation. And they couldn't, and they thought about, okay, we want to generate something similar to the sun, compressing hydrogen nuclei. So the idea came up to use a fission device. So you use a fission to generate enough energy to compress the light nuclei of deuterium and tritium. And in that case, you generate basically a star on Earth. 3 different ideas were suggested. One due to a scientist called Gamov. It's designated as squeezing the cat's tail. One by Edward Teller, the originator of the idea, called the womb. We'll see what it means by that. And another gentleman in the project, Stanislav Ulam, was a mathematician. He called it the spittoon. And they had to simulate those explosions on computers. So the invention of computers was really to simulate how to ignite a fusion device using a fission device. And that started here at the University of Illinois. If you go to the Coordinated Science Laboratory, that is where they built the first computer. They named it the ELIAC. Historically, the ELIAC was built here at the University of Illinois. And if you watch the movie Space Odyssey 2001 or read the book by Arthur Clarke, Space Odyssey 2001 again, or watch the movie, that was basically named in the movie called HAL. HAL stands for basically shifting the letters of IBM. All right, so the University of Illinois had a part in that, but we benefit as a spin-off with computers today. The idea was to use what's called a whole realm. That is a black body radiator. That's from, we have covered that material already. And it was suggested by the 3 scientists. And this is a picture in the book by Gamov describing the whole process of how to generate fusion having a fission device. Here are shown 5 personalities that were part of the whole effect. The United States had brought in scientists from all over Europe. One of them was named Fuchs from England, and he had ideological kind of ideas. So he leaked the secrets of how to design efficient device to the Russians. And the Russians eventually caught up on the United States. And what is shown here is Joseph Stalin, that was at the time the leader of Russia, carrying an atomic bomb. So the Russians basically discovered the process of fission, and they exploded their own device. Shown here is Robert Oppenheimer with a halo around his head, as shown as maybe an angel. He opposed the project, and it became a very nasty duel between 2 very strong personalities. Robert Oppenheimer, the director of the Los Alamos National Laboratory, it has been put into a movie, and this gentleman here, that is Edward Teller, who suggested that they should move beyond just the fission device, but go to the fusion energy release. He's wearing here what's called a NAHA. This is the device that they use in the American Southwest. And he suggested that maybe they should explode a nuclear device right here. And then the heat would be concentrated inside that ellipsoid of revolution in that case. The computer simulations on our ELIAC here showed that is not enough to ignite a fusion device. They cannot heat the hydrogen isotopes to reach fusion. Came in Mr. Stanislav Ulam, shown here, and spitting into a spittoon. You could see that spittoon in the cowboy or the Western movies at late night, where they chew tobacco in the bars or the saloons, to be exact. And then after chewing it, they spit it out, very ugly view here, into a spittoon, so they don't spit it on the ground. And Stanislav Ulam say, oh, maybe we should use this approach to from the fission device into the fusion part to explode it. And Mr. Gamov himself, who drew that diagram and put it in his book, the book is named The Curve of Binding Energy. Maybe you'll find it in the underground library or the engineering library. He was squeezing the tail of a cat. You see that? So he had 3 different approaches that he describes: spitting in a spittoon, using an ellipsoid of revolution, the geometry here, or pulling the tail of a cat. And Edward Teller describes and it seems that the combination of the 3 approaches was really the approach for achieving fusion from a fission device. This is a picture actually of that Navajo necklace worn by Edward Teller. And the end result is what is shown in that diagram. You use an ellipsoid of revolution. An ellipsoid of revolution is a geometrical kind of structure that has 2 foci, one focus here and one focus here. Any radiation of sound originating from this point reflects through the walls and gets to the other focus. So you had an open-ended ellipsoid of revolution that you would have now deuterium and tritium here that gets heated by the radiation from a fission device. And then the radiation generated from the fusion device goes into some foam that now is heated up to extremely high temperatures. It becomes like basically a plasma that concentrates or implodes a mixture of deuterium and lithium-6 in the diagram. Why lithium-6? Because the neutron generated from fission now would interact with lithium-6 in an equation that I gave you as an assignment and turn it into tritium. So in that case, you have deuterium and tritium, and the 2 of them are now at a very, very high temperature through compression by radiation. They fuse together. And notice something interesting here is that you can make that part of the device as long as you can. It's almost like igniting the tip of a cigarette. So in that case, in a fusion device, the yield can be made huge. You can make it very small, right? If you take only that part, but you can make it infinitely large. And it acts more like a multi-stage amplifier, like you had in your classes in circuit analysis. You start with fission, you ignite fusion, then they surround the whole device with a casing made out of uranium-238, and the neutrons, as you calculated in one assignment from the fusion of deuterium and tritium, carry a very high energy, 14 million electron volts. So they fission the uranium-238. So you start here with, say, a 10 kiloton of energy, and in the fusion part, you can end up with 10 million tons of energy, and it's a multi-stage device. This is a drawing that I tried to put myself. You'd have, what's missing here is that you must have a shield between one focus and the other. And what is missing here also is the part in the center that they call the spark plug, made out of plutonium-239 or uranium-235. You compress the fusion fuel, and neutrons also explode or fission that plutonium-239 or uranium-235 in the shell. Initially, they were thinking that they needed to use lithium-6, but later on they discovered that all they needed is just plain lithium. So they went in the wrong direction because they didn't realize the equation that I wrote on the board last time, that you also can breed tritium from lithium-7. And as I suggest here, in between the casing of uranium-238 and the fusion part, you would have basically foam, polystyrene foam that generates the plasma. You add to it some material like a heavy element, like iron dust, so that one would stop all the gamma radiation and the X-rays from the fission device. That configuration became known as Ulam-Teller configuration, and variation of it are used by what the nuclear power states of the world now have. They don't stop at the simple fission device. They always go to generate more energy. Mr. Robert Oppenheimer suggested that by spiking any fission device with some deuterium and tritium, you can generate enough fusion to multiply the energy release from the 10 kilotons, say, to 100 kilotons of energy, because that is all you need to destroy any strategic kind of military targets. Edward Teller was not of the same at the same wavelengths. He accused Robert Oppenheimer of being a traitor because he had a friend in California. California at the time was a very liberal state who was a communist, and Oppenheimer was stripped of his security clearance. He was humiliated, and Edward Teller got his way. So it was a very big struggle between two very strong personalities. Edward Teller, in fact, went to the Air Force, and the Air Force built for him a whole laboratory. The Lawrence Livermore Lab was built by the Air Force so that Edward Teller would achieve his idea of the super. Stanislav Ulam wrote in his book, you can find it maybe in the library if you are curious about the history. The title of the book is Adventures of a Mathematician. I quote here, perhaps the change, because they didn't succeed really. The computer simulations showed that they could not ignite the fusion part like a star by the fission. But according to Stanislav Ulam, perhaps the change came with an idea I contributed. I thought of a way to modify the whole approach by injecting a repetition of certain arrangements. Unfortunately, the idea or set of idea involved is still secret and cannot be described here. So we can only guess about how that Ulam-Teller configuration is, and combination of it are part of careers that people spend really designing those nuclear weapons. So the main reaction for fusion reaction in that case was a reaction between two isotopes of hydrogen, heavy isotope deuterium and tritium. deuterium is abundant in our water and in our oceans. And tritium, though, does not exist in significant quantities on Earth. Some of it is trace amounts from cosmic radiation, neutrons interacting in the atmosphere, but we have to breed it from lithium. So it creates for us here today a resource problem. We are using lithium in storing energy in the form of batteries, the lithium-ion batteries. Everybody using a computer here has one, or a phone, lithium-ion batteries, but deuterium plus tritium became the main reaction, with tritium being bred from lithium. The reaction generates a neutron with very high energy, 14.06 million electron volt. If you compare this to the energy of a fission neutron, it's only 2 million electron volt and an alpha particle. And this was the basis, basically, of those fusion reactions. And on the other hand, it will be also the basis of the first generation of fusion reactors that we are going to be building. Why that reaction is easier to produce on Earth. Once we learn about it, you'll find that we can do better than just a reaction between deuterium and tritium. I'll give it to you as an assignment maybe today. You can only fuse deuterium just with deuterium. So in that case, you don't need the lithium breeding the tritium, and the water in our oceans becomes our source of energy. Would be practically using water to produce energy. Deuterium to hydrogen, the ratio, at least on Earth, is 600 parts per million. So every million hydrogen atoms, that's 600 deuterons, both in our oceans, our lakes, water, and then even in our own body. They had to test the idea. So on the Marshall Islands, they built a cryogenic device. And in fact, the first test here used that concept of the deuterium. So they got the deuterium and they liquefied it cryogenically. So they built a large cryogenic factory here, placed the deuterium in that big container, and then placed inside it several fission devices and to test whether they can generate fusion out of fission. Look at the size of the device. Look at this gentleman there sitting there on the ground that had all those tubes several miles away from an island in one of the Marshall Islands to check what is released from the explosion. And that device was named, well, actually, this is the configuration. It shows that spark plugs that I mentioned before. They had a fission weapon here on the top. So it's an Ulam-Teller configuration. And then the fusion charge was here at the bottom. And they tested it in the Enuitak Atoll, I think, or the, again, this is the picture of an atoll here, coral reef forming a ring as an island with an opening to the sea. So they exploded here inside the atoll in the Pacific Islands. And that was in 1952. And it was a monumental success, if you want to call it. They call it the Ivy Mike thermonuclear test. And it yielded 10.4, not kiloton, but megatons, millions. So the energy release from fusion is not twice or 5 times or 10 times. No, it's 1,000 times what you could release from fission energy. Yes, that was the Enuitak Atoll, not the Bikini Atoll. And that was in October 1952. The cloud here from the explosion reached 100,000 feet in height in the atmosphere. And basically, you can check it with the site of the Department of Energy. They may have some interesting information. At that time, they worried about something very interesting. What if the energy release would ignite our atmosphere? Our atmosphere, as you know, is primarily nitrogen. 70%, what we breathe is 70% nitrogen, 15% oxygen, some CO2 and other gases. But they worried that, oh, what if we release that energy and we just don't ignite deuterium and tritium, but we ignite the nitrogen in our atmosphere and the Earth would become a star? Well, they did calculations, and luckily, as you could see, it did not happen. So otherwise, you wouldn't be here. They worried about the nitrogen 14 plus nitrogen 14, generating magnesium 24 and alpha particle. As I suggested, the use of deuterium as a cryogenic hydrogen, liquid hydrogen at cryogenic temperatures is not really something that you can turn into a portable or a deliverable device. So the Russians started by testing lithium deuteride. What's lithium deuteride? Deuteride is hydride, so it's lithium hydride. If you have lithium hydride, it's a powder. So in that case, it is not operational at cryogenic temperatures. So they built that device here, what they call the Bravo test. A picture of the device is shown here. And the suggestion is that it's a Ulam-Teller configuration now with a spherical fission device here with a long cylinder of the fusion part. So that would be the trigger, that would be the charge. And you'll find that, as I suggested, 80%, they generated the fusion, and then they had a tamper, or surrounding it was a casing made out of uranium-238. And that uranium-238 released 80% of the yield. But the interesting aspect of it is that it is now a deliverable device, something you can put on an airplane. Otherwise, you cannot have the deuterium plus deuterium fusion because it would have to be cryogenic. And look what happened in that case. The device was huge. Look at that gentleman there. They placed it on a barge, and they exploded it inside the Bikini Atoll shown right here. Something tragic happened in that the meteorologists made a mistake in suggesting where is the direction of the wind is going to happen. They thought it will go into the Pacific Ocean to the west. Instead, over 5,000 miles, it went to the east, where there were islands with populations, and not only a population, there was even the yield from the device came out twice what was expected from it. And because they thought that's what only lithium-6 that is going to generate the tritium. But in fact, we know today that both lithium-6 and lithium-7, they didn't need to separate lithium-6 from lithium-7. Both of them produce tritium. The energy release was so huge that it affected the bunkers where people were observing the test. They had to be evacuated by helicopters with bed sheets basically covering their heads. And that was also there in the Bikini Atoll in that case. If you visit the Republic of the Marshall Islands, you can see that sign. Maybe you can have a chance. What was not known at the time is that there were observation ships, the Curtis here, that had a crew that was exposed to the radiation. And the Lucky Dragon was a ship, a Japanese ship that basically saw dust coming from the sky in the middle of the Pacific Ocean. They thought it was snow. One sailor died in it. It's kept in a museum apparently in Japan, and that was at Bravo test. And they had to evacuate the people in those islands that were affected by the fallout. I give here a tentative explanation. As I suggested, the yield came in more than they had calculated, 3 times their calculation, in fact, not just 2 times. And in that, again, they ignored the breeding in lithium-6 and lithium-7. We know better today. And in fact, I gave you those 2 equations to balance and maybe to calculate the energy release from them. That's left for somebody who wants to work on a PhD and so on. And in that case, the nuclear age now was born. Let me just finish that part. And this is one of those devices that were built, the Mark 17, a thermonuclear device. Look at how large it is. It had to be carried by very large aircrafts. However, today, it's all miniaturized. This, you could see here, that's now the W80 warhead. It can be carried by 2 people. This definitely is the fission part, and this would be the fusion part, and it can be carried on a cruise missile. So here We are living in a world where the release of energy is not in the thousands of tons of TNT, but in the million of tons. And I invite you to read the rest of the chapter. We'll finish it next time. Have a nice weekend, everybody.